Hey everybody, welcome to our next short video lesson here, and today we're going to talk about isomers associated with alkenes. So I've got a white space here because I'm going to use this to show you some models, and then in the second part of the video, I'll go back to my iPad and we'll look at specific structures and we'll go through some of the nomenclature in greater detail. So we're talking about alkenes, so we're talking about molecules that have a double bond. Now, a couple of basic structural features to remember about alkenes. So the six atoms I'm showing here, they're all in the same plane, right? So this molecule, as hopefully you can see, is entirely planar. That's because both of the carbon atoms are sp2 hybridized. So they both contain a trigonal planar geometry. Both carbons are trigonal planar, all right? So the whole molecule around the double bond is going to be flat. Now, the fact that it's flat means that it could have a structure that might look something like that, where in what I'm showing you here, I've got two greens at the top and two whites at the bottom, or it could have a structure that looks like this, where there's one green and one white, and one green and one white. And the important thing is that when it comes to alkenes, that double bond, it doesn't rotate. Just like the molecule is resisting my attempts to turn it, the double bond, it doesn't rotate. Contrast that with, say, an alkane, which has a carbon-carbon single bond. And so these carbons, they're tetrahedral, and so they have sp3 hybridization. The carbon-carbon bond here, just as this model shows, it freely rotates. I can twist these carbon-carbon bonds all day long with very, very little difficulty. So we don't have isomers. We don't have kind of locked-in positions like we have here for alkenes. We don't have that feature for alkanes because of this free rotation. Now, in a later video, we're going to talk about isomers that can be associated with tetrahedral carbons. We'll get to that in a little bit. But I want to focus, again, on this difference that I have between structures like this. All right, so there's two levels of terminology that I'm going to go into details here and in further detail in the notes. The first bit is the use of the term cis and trans. So we have here two different groups off of each carbon. I have a green group and a white group, a green group and a white group, okay? If the groups are fairly simple groups, let's say these green atoms represent chlorine atoms. So I have some version here of 2,3-dichloroethene, okay? Or excuse me, 1,2-dichloroethene. So carbon 1, carbon 2, so it'd be 1,2-dichloroethene. So I can have this version where the chlorines are on the same side of the double bond. So if I think of the double bond like it's a fence, the chlorines are on the same side of that fence. This would be referred to as the cis isomer. The other example here, if I have the fence of the double bond, the chlorine atoms are on opposite sides of that fence, that would be called the trans isomer of the 1,2-dichloroethene. And again, since they can't rotate very easily, these are distinct molecules. They'll have distinct properties like different boiling points. They'll have distinct reactivities if we went into that level of detail. All right. The other nomenclature that we have associated with alkenes is nomenclature that's actually based on some German terminology. Let me go to my cis isomer here. Let's say, for example, that these chlorine atoms weren't chlorine atoms, but maybe they represented some longer carbon chain coming off, and maybe it was really complicated. And so the simplicity of two identical groups being on one side of the double bond is no longer there. Things get a lot more complicated. In that case, what you do is you assign priority to the groups off of each double bond. So you would look at each carbon of the double bond by itself, and you would say, okay, which of these two groups is of higher priority? And there are rules for determining that, and we go into that in the notes. But let's just, for color simplicity, let's say that we decide that the green group is of higher priority. So this is higher than that. Then you also look at the other end of the carbon-carbon double bond, and you need to determine priority. And again, for simplicity, let's say that the green is of higher priority than the white. So then here, I have the two higher priority groups, again, on the same side of the double bond. In this alternative way that we use nomenclature, this would be referred to as the Z isomer. Okay, and Z comes from the German word zusammen, which means together. So the higher priority groups are together on the same side of the double bond. The way I always have remembered this is I think of Z as same side. Hopefully that helps you. So if the higher priority groups are on the same side of the double bond, that would be the Z isomer. This version of the same molecule, where the higher priority groups are now on opposite sides of the double bond fence, this is referred to as the E isomer, and that comes from the German word entgegen, which means opposite. So the higher priority groups, these two greens, are on opposite sides of the double bond fence as it is, and so that's the E isomer. So we could call that cis or Z, or we could call that trans or E. And typically for IUPAC rules, we're going to prefer the E and Z bits of nomenclature because for reasons I go into greater detail in the notes, E and Z is less confusing, less ambiguous than cis and trans. One last thing I want to point out, notice the differences between these two molecules. On the molecule on the right, I have two different groups on both ends of the double bond. If I'm going to have these cis or trans or E or Z isomers, I need different groups on both ends of the double bond. In the molecule on the left, I have different groups on the bottom carbon, but I have identical groups on the top carbon. This molecule on the left cannot have E or Z or cis or trans distinctions, because if I go ahead and make another version of the molecule, right, so I have there two versions of the molecule, we'll see that these are actually the same molecule. All right, they are identical in every conceivable way. So if one side of the double bond has identical groups coming off of it, cis trans EZ is not an issue. You don't have to worry about that nomenclature. But if you do have entirely asymmetric double bonds, again, two different groups here, two different groups there, then you will have to include cis or trans, or as we will prefer as we continue through the E or Z nomenclature. All right, so I'm going to turn this over to some examples that we'll look at in more detail, and we'll wrap up this video. Okay, so let's go ahead and start taking a look at some examples of the EZ isomers associated with alkenes. So taking a look at this structure up the top, we have a highly halogenated alkene. So I've got two carbons in there, so this is going to be named based on ethene. Now with all these halogens around here, the question becomes, is that carbon one? Or is that carbon one? Well, we know that bromo comes first in the alphabet amongst all of these different halogens, so we're going to defer to the carbon on the left being carbon number one. All right, so if we were to go ahead and write the name out, actually, sorry, before we do the name, let's assign the E or Z of it first. So on the left-hand side, I'm going to compare a bromine to a fluorine. Bromine has the higher atomic number, so the higher priority group is the bromine. On the right-hand side, I have chlorine versus iodine, and the iodine is going to have the higher priority. So the higher priority group is there. So the higher priority groups then are on opposite sides of the double bond, right? I like to think of the double bond as a fence, so they're on opposite sides. So that's going to be the E or entgegen or opposite isomer. All right, so then we put that E out in front of the name, and since there's only two carbons in this alkene, I don't really need to put a number here, so it's just going to be called E. And then on carbon number one, I have the bromo. On carbon 2, I have a chloro. Again, doing alphabetical ordering. I'm going to shrink this down a little bit so I can get everything to fit. 2 chloro, 1 fluoro, and then shrink it down a little more. Sorry about that. 1 fluoro, 2 iodo, and then it's going to be ethene, ethene. Okay, ethene. All right, so E, 1 bromo, 2 chloro, 1 fluoro, 2 iodo, ethene. All right, let's take a look at the next problem, okay, the structure here. So let's go ahead and do the RNS. There's my double bond. I have a hydrogen versus a carbon. So right away I have a difference. So the carbon is the higher priority group. On the right-hand side, I have carbon, carbon, so that's a push. There's no difference there. Then I go to the highest atomic number atom off of that carbon, which is going to be that nitrogen. Here, the highest atomic number atom off of that carbon is another carbon. So I have carbon versus nitrogen, and so the nitrogen wins, and so the higher priority group is going to be up there. Again, look at it with respect to that double bond fence, and we see that we have the two higher priority groups on the same side, on the Z side of the double bond fence. So this is going to be a Z isomer. All right, so let's go ahead and try to write out the whole name then. I'm going to have, on carbon number 2, I'm going to have a Z. So that carbon, that double bond starts on carbon number 2 because carbon number 1 is right here. There's carbon number 2. Okay, and then I'm going to have 2Z. Then also off of carbon number 2, I'm going to have this branch. And since it has a bromine on there, I'm going to need to use parentheses because on the second carbon of that branch, I have the bromo. And that is an ethyl branch. So that is overall a bromoethyl branch. And then on carbon number 2, that's where I have my butene. My double bond ene is on carbon number 2, and then I will call it 2-butene, and then it's 1-amine. All right, so overall that is 1, 2, 3, 4, so that's why it's a butene. On carbon 1 is my amine, and then I have that branch right there, that is the 2-bromoethyl branch. So 2Z2, 2 bromoethyl, 2-butene, 1-amine. All right, okay, so then let's look at the next example here. All right, so carbon number 1 is going to be right here. So I'm going to have 1, 2, 3, 4, 5, 6. So this is a hexadiene, diene for the 2 double bonds. Now, since I have 2 double bonds, I have to assign priority to both of them. So let's go ahead and zoom in so we can do the priority. So let me see if I can divide this up a little bit. So I've got the 2 sides of the 2 double bonds. So looking at this side first, I'm going to compare a carbon to the undrawn hydrogen, right? There is technically a hydrogen here. And so that carbon will beat out the hydrogen. On the other side of the double bond, I have that carbon that's going to be compared again to another undrawn hydrogen. So this carbon wins out there. So with respect to this particular double bond, I have opposite sides. So that then is going to be an E double bond. All right, let's see if I can erase all this mess, or at least some of it, so we can zero in on the other double bond. All right, so on the other double bond, I have again an undrawn hydrogen here. So I'm going to compare this carbon with that hydrogen. So this carbon wins. On the right side or right end of the double bond, I'm going to have a nitrogen versus a carbon, so the nitrogen wins. So then with respect to this double bond, the 2 groups there are on the Z or same side. So one of the double bonds is Z, one of the double bonds is Z. And again, since carbon number 1 is this carbon here, and we're going to number it right to left. So putting all of this together is going to give me the following name. I will get, in parentheses, at carbon 2, there is a Z alkene. At carbon 4, there is an E alkene. And then I'm going to have 2-azeto, 2,4-hexadiene. All right, I've got the 2 because I've got the 2 double bonds at the 2 and 4 positions. All right, so all together, 2Z4E, 2-azeto, 2,4-hexadiene. So I had to assign stereochemistry, E or Z, to both of the double bonds. All right, I've got this structure here, but this is actually a little bit of a trick question. See if you can understand why this is a trick question with respect to E and Z as I start to talk about how to number and name it. In terms of numbering, we're going to start here because we want to get the double bond the lowest number possible. So I'm going to have a 1-ene here, and then it's 1, 2, 3, 4, 5. So this molecule is going to be named 1-pentene. Now, coming back to E or Z, I don't have to do E or Z here. Why is that? Because on the right end of this double bond, what do I have here? I have 2 undrawn hydrogens. So on the right-hand side, I'm not going to have any priority. Hydrogen is tied with hydrogen. In order to have E or Z, if you recall from the earlier part of the video, in order to have E or Z, you have to have a fully asymmetric double bond. Both ends have to have different things up top and down bottom of each end of the double bond. All right, I've got one more problem here. And I threw this one in because this one's kind of sort of a long, fun name. And what we have here is an example where I have an ester functional group. I have an alkene on the parent chain of the functional group, of the ester functional group. But I also have an alkene off of the side chain off of the ester functional group. So this one's going to get into some nomenclature we haven't seen before. I wouldn't worry too much about getting the details of this one down. I just wanted to throw this one in because I think it's kind of fun. But first, let's go ahead and do E or Z. So over here, I've got my double bond. Carbon beats hydrogen on one end. On the other end, oxygen is going to beat hydrogen. So I have the higher priority groups on the opposite ends, on the opposite sides of the double bond. So this is going to be an E alkene. On the other alkene, I have a carbon and a carbon. That's a tie. Off of this carbon, the only thing I have is hydrogen. So I'm going to compare a hydrogen to the highest atomic number atom attached to this carbon is another carbon. So this chain will have higher priority than that chain, so down below. And then on the other end of this double bond, I'm going to compare a carbon to the undrawn hydrogen. So I have the lower end on this side and the top end on that side. So once again, I have them on opposite sides of the double bond. So that, again, is an E isomer of that alkene. All right, so if you remember, when you name esters, the first thing you're going to identify in the name is the alkane branch, or the R branch off of the singly bonded oxygen, this stuff over here. So then I need to identify all the component bits on that part. So that part of the molecule contains an E alkene, so I'll put that first. And that E alkene shows up on carbon 1. So that'll be carbon 1, 2, 3 of the chain. So at the 1 position of the 3 carbons, I have a propene. But since it's the side chain off of the ester, I still include the YL ending, as is appropriate for the beginning of the name of the ester. So the whole beginning of this is E1 propenyl, and then I'm going to hit the space bar, so I'll just emphasize that by showing a space there. And then I'm going to name now the rest of the parent chain side of the ester. And so at carbon number 3, I'm going to have an E alkene. And then let me just shrink this down to continue fitting it in. Come on, shrink down for me. There we go. All right, so 3E, and then I have a methyl group on the 3rd carbon, right? 1, 2, 3, so there's a methyl group on the 3rd carbon. And then at the 3rd carbon, I also have that double bond, so I need to put that in the parent chain name. So that'll be 3-pentene. And then I have the O8 ending for the ester functional group. And of course, I could slip in a 1 there if I wanted to, but with esters, the carbon that starts the ester has no choice but to be on carbon number 1. Okay, so there are 5 examples of naming alkenes, and I don't know why that part of the name stuck out there, but there are 5 examples, and so hopefully you can look at the worksheet and get through most of that.